Piecewise functions are one of the simplest yet versatile nonlinear functions composed of multiple linear units. These kind of functions are easy to understand as well. Piecewise functions are everywhere, from linear spline interpolation, bilinear interpolation, decision trees, ReLU based neural networks, and many more. In this video, we will explore the one-dimensional piecewise functions and play with them. We will get into piecewise functions from ReLU based MLPs, then move into piecewise linear function. We devise a method to convert piecewise function to MLP and decision tree. These explanations will be covered in writing code and visualizations as well. At the end, we superficially touch higher dimensional piecewise linear functions. The link for the code is in the GitHub repository mentioned in the video description. So let's get started. When we think of a function, a machine comes to our mind. This machine takes some x and gives output some y. This can be written in an equation as y equals to fx, or in a block diagram as shown here. Some commonly used functions include linear function, that is y equals to mx plus c, and in the vector form we have y vector equals to w dot x plus c. Similarly, the function can be a polynomial function as well. The polynomial function takes the form y equals to a0 plus a1 x1 plus a2 x square plus a3 x cube plus so on and so on. There are other parametric and exotic functions that is used a lot in machine learning, such as neural networks, decision trees, splines, etc. In this video, we are going to focus on the piecewise functions, that is piecewise neural networks, piecewise spline, and piecewise decision trees. We have covered how MLP works in a previous blog post. If you want to check that, the link is in the video description. Next, we'll look how piecewise multilayer perceptron or piecewise neural network work for one dimension. Let's take a simple computational graph of a linear transform. It multiplies x by w and adds bias to get y. So linear transformation can be represented by y equals to linear of x. And if we perform the linear transformation twice, it is still linear. So there is no nonlinearity introduced. If we want to introduce nonlinearity, we can introduce it in the intermediate variable in the g. So a choice of nonlinearity could be sigmoid, 10h, or ReLU, that means rectified linear unit. Since we are working with piecewise functions, ReLU will be the best choice for us. Let us consider a one-dimensional multi-layer perceptron with 3 hidden units, and on 2 of the hidden units there is railway activation function. We can see on the right that 3 different type of pieces are formed, and these pieces when added together produce our desired function. The job of the bias is to shift the function up or down. These pieces are actually guided by the parameters, and if we have different parameters, we can produce a different looking piecewise function. For the 3 pieces, we can have something like this, a different function. And if we increase the number of neurons, we get more and more pieces. We can see that piecewise functions are actually lines connecting the breaking points. However, multi-layer perceptron creates piecewise function by adding multiple piecewise functions, which is difficult to interpret. There is piecewise linear function or piecewise linear spline, which define piecewise function using the breaking points. And if we change the breaking points, we change the function, and it is easy to understand. Next, piecewise linear splines. Piecewise linear spline is a collection of linear functions defined over different intervals. The function is independent of other intervals and is easy to understand. Consider a set of points that make piecewise linear spline. The 3 points are x0, y0, x1, y1 and x2, y2. Connecting these 3 points using a line, we make linear spline. We get equation of line for each piece, and the equation of line given 2 points can be derived using the formula y equals to mx plus c, where slope can be again derived by using dy upon dx, and the y-intercept can be found by shifting the points to origin first. That means subtracting x0 from x and y0 from y, and in the equation we get y equals y1 minus y0 upon x1 minus x0 times x minus x0 plus y0. So this would be the equation of line given 2 points. Using this equation, we get output y0 at x0 and output y1 at x1. So here we define the piecewise linear function using multiple pieces of lines in the given intervals. Let's get into some code. First, we import numpy and matplotlib. We are going to interpolate over these points using polynomial function linear and cubic spline, dysentery, and neural network. First, polynomial spline or polynomial function. So polynomial function will fit the points in this way. Let's try cubic and linear spline. So here is cubic spline and here is linear spline. Linear spline is a piecewise linear function. Let's try dysentery. And this dysentery is constant output dysentery. And it also touches all the points. And for the neural network, we use our neural network made from scratch. Not to think much about it, we use 6 hidden layer and ReLU activation function for a single layer neural network, single hidden layer neural network, and this is the optimization process. So the neural network is fitting to these data points. Yes, we can see here the interpolation goes out of the data points, right? This can happen in neural networks. Let's see all of them at once, and we can basically find the exact difference between neural network and linear spline here, because neural network goes away from the data point here, but linear spline just connects the dot. We cannot say any one of them is better than the other because all of them are the same, because all of them connect the given data points. So every interpolation is equally valid, and it might depend upon the problem you are tackling. So let's get into Piecewise Mlp. And before that, let's see how changes in parameter affect the ReLU function. It is of individual neuron and how the parameters affect it. Okay, you can see here that weight first W1 changes the direction of the slope. Either it is in negative x or positive x. The first bias changes the breaking point in x, and W2, the second weight, changes the slope to be upward or downward, right? And the second bias changes the shift in y, and these can be combined to form any nonlinear piecewise function. So let's try to fit Mlp. Let's try to fit Mlp on this synthetic data set. So let's create a neural network and train it. So here is the visualization. And it's training, and each dotted line is the neuron, right? Individual piece. As you can see, some neurons are facing downward, some are facing upward, some are breaking to the left, some are breaking to the right, and these all combine to make neural network. These all combine to fit the data and make this piecewise function. So let's see how PWLF, piecewise linear fit, works. And piecewise linear fit works on different kind of optimization. Piecewise linear fit works with different kind of optimization, and here we want 5 pieces. So it is fitting now, so we can see how the plot looks, and it has fitted the chord with these breaking points and the line connecting them. So it is simpler to understand, right? For 1D. and we can compare the plot here, and we can see both of them produce piecewise function, and there is some difference in the fit. We can also see that the error is very low in both of these models. Next, our goal is to convert PWLF function to ReLU based MLP. In this way, we understand both PWLF and ReLU MLP. So first, let's calculate the slope of the PWLF. And here we find the slopes, and we can agree that it's 4, minus 0.7, 0.2, 2, and minus 1 point something, right? And we can also check the breaking points. Minus 1 point something, 0.7, 0.3, minus 0.3, 0.2, and so on, right? There is also y breaking points, and these combine to make piecewise function, right? Now we know from the figure, right, from up here, the ReLUs make these all sort of pieces, broken pieces. These are ReLUs. These are ReLUs, and these add up together to form this kind of function, right? It is linearly dependent on each other. So how are we going to tackle this problem? A piecewise function with 4 pieces like this one can be converted into ReLU based MLP, and for that our strategy is to find the breakpoints and start from left to right, adjusting the additional slope, right, making the slope dependent on previous slope. So for the first piece, it is easy. It's a ReLU with the exact same slope. But for the next slope, we compute the slope added with previous slope. That makes the desired slope, right? So here we add a slope that goes down, way down, to make for some downward slope. And similarly for the next slope, we add a small slope smaller than the required, because the previous slope is already pointing downwards, and we'll get a downward pointing slope, right? And the next slope is going upward, so we want to accommodate the downward slope by adding a lot of upward going slope, and we'll get the desired slope. And the top portion is the piecewise linear function, the bottom portion is the multi-layer perceptron. First, we can simplify the process of constructing piecewise function as starting from left and going towards right, breaking each point and breaking at each point to generate next slope. And to do that, we start with first slope, right? We make the slopes dependent on each other. Initially they are independent and we are making them dependent. So we can see the slopes 0.43 at first, right? And but it goes minus, because to compensate for the high rise in slope, we make high fall in slope, and these add up together to form minus 0.716. And again we add this much slope to make 0.2, and we add again 2.14, and we again add 2.147 to make 2.35, and so on. It works like that. So for that, we can since we start from left to right and only go a rightward slope, right, only go the slope that goes right and up or right and down, so it always goes to right, the ReLU always goes to our right in our case. So for that we don't want any slope, we just want the breaking point. For that we put the slope 1 for all neuron, and in the breaking point we start from the first neuron, the first breaking point, and we can ignore the last breaking point, and the shift up or down of the breaking point depends upon the first breaking point of Y. So doing so we get W1, W2, B1, B2, right? If we forward propagate with that parameter, we get this output, and we can see both produce the same result. And we can see the individual neurons, right? How we designed it and how it happened. So the first neuron starts from 0 and goes upward, right? But it is multiplied by slope that we have found out. So, and it is multiplied by the slope 4 point something, right? And another, he starts from here, and the downward it is minus 4 point something to make this slope, and these add up. Like here the neuron makes it like this, and this neuron makes it go up, and this neuron make it go down, and it makes a multilayer perceptron. So yeah, and furthermore we can also convert this piecewise function into decision tree. The decision tree will have linear, like it will have a line as a output node with M and C for Y is equals to MX plus C to define the line. So each piece can be represented by a leaf node, and to get to the leaf node we can start from one of the breaking points and go left or go right to find the leaf. So here is the decision tree. Here it compares if the given value is less than the breaking point, right? And in the leaf node we have slope and intercept to make the line, and in the decision node we have the question and true runs and false runs, right? And we have a function to print the tree. So these functions are copied from internet, and I couldn't find the reference. So this function makes tree from PWLF, and what it does is starts from the given the breaking points and the indices, it breaks the middle point and puts left and right points to make a tree in a recursive fashion, right? And the midpoint would be a question. So doing this recursively we get decision tree, and we convert it into decision tree, right? And we can see that the decision boundaries are given by these lines in the breaking points, and let's see how the tree works. So if x is less than 0.37, right, 0.37 here, and if it is true, then it acts if it is less than 0.75, right here, and if it is true then we get equation of line there, this line. If false we get equation of this line, right? And for the top node, root node, if it is not less than 0.3 something, then it goes in this direction, and it asks if it is less than this. If yes, then we get slope of this line and equation of this line. If it is false, it asks if it is less than this line. If it is less than this line, you get equation of this line, and if it is greater than this line, we get equation of this line. So we made a decision tree out of it. Not much useful, but we get the point, right? These functions are convertible from one type to another. It opens us to various questions as to if we can convert complex functions from one to other. And there are distillation based methods, which I'm not going to talk now, but they can be converted, not exactly, but to some extent, yeah, it is possible. So let's get into 2D piecewise functions. What we dealt with is one-dimensional, and this conversion is not exactly possible in two-dimensional piecewise function. So let's see how piecewise function works in two-dimensional. First, we make a 2D grid. You can see the axis, and y is like sines and cosines. We can interpolate it using the given grid, and for that we use SciPy interpolate 2D, and we get something like this. So it is interpolated from the given point, right? Here the points are very dense. So this is two-dimensional interpolation, and we can also see the surface that formed from the interpolation, right? From linear interpolation. So we can do 2D interpolation as well. So we can also perform interpolation using decision trees. In 2 dimension, I have found a resource on the YouTube.
Start with the root, a single estimate that roughly fits the entire data set.
So here you can see the data is fit recursively using decision tree to the given data point, right? So you can check it for yourself. We'll not go into that. So next we'll go into Mlp based piecewise function for 2 dimension. Let's generate a synthetic dataset at first, and you see this is a 2-dimensional dataset, and we want to fit a piecewise function to this dataset, right? So we make a neural network with 10 hidden units and relay activation function, and here is the learning process. Yes, so this piecewise function is being fit to this given data. It is taking some time, but you can see here there are multiple pieces, and a ReLU based MLP produces such piecewise function, right? You can see here there are pieces. There is one piece like this one, and here is another piece like this here. So we can extract these pieces by looking at the weights and bias, because we can convert these weights to the equation of a line in a 2D plane, and doing that we get the lines, and it is plotted here. So these are the decision boundaries at axis equals to 0 for the ReLU, and all of these combine together to form the pieces. Here is one piece, this is one piece, this is one piece, and this is one piece, and so on and so on. These all points are pieces. And for comparison, yeah, so first thing, if we look at the plot, x1 and x2. The line goes from -1 towards another end, right? And here, this is the line, like this goes here and here and here, and in the middle there is an intersection, right? Here intersection between all these lines. All these pieces make this function that fits the data. We could have put more neurons, but it would be difficult to visualize. So yeah, piecewise function 2D in 2D, and we can see the gradients that are different for multiple pieces, and if we plot it here, we can see that the gradient of a piece is same because it is a piecewise function, right? And it is discontinuous as well. So if you want details for multiple layers and how piecewise linear activations work in deep neural networks, check out this paper. Here is the link. Thank you.